used to it, McKinley, if you get married.
Especially to her.
Oh my gosh.
Yeah, we played a game of match today, and both of them got to each other.
In whose class?
Ours.
No, which
Oh,
class?
we played in science.
Oh, science.
Yes, but also Anna and I both got each other.
Yeah, McKinley dies at 6.
Anna and I have 18 kids within the span of a year.
Oh, good God.
Most of us are dying at 15.
Anna's going to die.
I'm gonna die because I have to have 18 kids in a year.
Yeah.
I'm adopt all of them.
You've got like 1.5.
All right. Now, your homework was 1 through 17. Any questions? There was mostly drawing. What's up?
I have a lot of questions. 18.
A lot of questions?
Yeah.
All right. Which one?
5?
Yeah, the other class had question 5 too.
I was just confused on if there were supposed to be 2 separate circles or one.
Oh, just 2
So-
concentric circles.
So the radii have 2 concentric circles. What's a concentric circle?
Where there's circles.
They share the center. So doesn't say what the relationship of horrible circles, but you get the idea. But they share a center. Okay. So the radii of 2 concentric circles are 15 and 7. So clearly this would be your 7, and that would be 8, total 15, right? Got that part? All right. A diameter AB of the larger circle, diameter AB of the larger circle, so AB of the larger circle, intersects the smaller circle at C and D. Intersects the smaller circle at C and D. All right. Find 2 possible values for AC. Well, clearly one of them's got to be what?
8.
Well, 8 would be from here to the center. So they're saying AC though.
But 8 is from the outside to the.
No. 8 it was 15 was the radius of the larger one. So 8 is just from here to here.
Yeah.
Right. So then 15, 8 is.
Oh, you're right. I'm wrong. Never mind. You're right.
Yeah.
All right. So 8. Now, why did they say 2 possible values?
Because you could either have a B and D switch.
See that? Right. I put C there and logically going in alphabetical order. But if I change that to right here, now that's C, that's D, then 8 plus 7 plus another 7. Right, 22.
22 or 30.
What's that again?
22 or 30.
No, we were right the first time. 8 or 22.
8 or 22? Oh, okay.
Because
yeah.
it's 8 if I put C here, but if I put C here, it would be 8 plus 7 plus 7.
No, but it's the distance AB.
No, AC.
Oh, okay, that's where I messed up.
No, you were right. It is 8B.
It is?
No, it says AC.
No. Boy, we're both triple wrong here. It is AC, yeah. Possible values for AC.
I
So
got
8.
22.
The other one's 8. Okay, so there's 5. They had the same question.
I have another one. 8. I couldn't figure out how to put the obtuse.
So an obtuse triangle. So, so whoa.
That's a quadrilateral.
There's my obtuse angle. So the circle is going to wind up not like this, but like this. So, well, because if you put it down there, then this vertex wouldn't touch.
I just made a right triangle and said it was 91 degrees.
No, it said obtuse triangle.
Which is obtuse. 91 is obtuse.
So it's not a right triangle.
Exactly.
So why did you say right triangle?
I just made it a bit bigger than.
Oh, okay. Oh,
And
so
it
you
fit.
made a quasi right triangle. I got you.
And it fit.
Yeah. Anything else?
8.
Okay, so we're back to concentric circles again.
They don't have to do those.
Congruent or says it concentric? Oh, you're right. Congruent. Draw 2 congruent circles with radii of 6, each passing through the center of the other. So center, center, right? So is it radii or diameter of 6? Radii of 6. So if this is 6, right, and they have to go through each other, then that means that actually the line is going to go from there to there is 6. So there to there is 6 as well too. So when you draw your circle, Oh, that's bad. That is not even remotely
That
close.
looks actually a lot like.
Thank God I don't have the recorder on, but yeah, that's the idea.
And then you can figure out the.
Is there a question after that?
Yeah.
Find the length of the common chord. So what's a chord? Common chord. Well, a chord has to go from to there.
Right.
So how in the world are we going to find that?
Well, you want me to tell you, or do you want me to let you?
Go ahead.
Well, it's a kite. Well, you make it look like a kite, but it's actually a rhombus.
It actually is a rhombus. Right.
So when you.
And the reason for that is because here's a point on this circle. So if I were to draw a radii, then it's, if that is 6, then this has to be 6 as well because they were common radii. Right. Therefore, this piece has to be 6 and that piece is, so it's actually not a kite, it's a rhombus.
Yeah, that's what I was saying. You make it, I said it looks like a kite, but it's a rhombus.
Yeah.
So, and
then the chord would go, or the diagonal would go here.
And then you can figure that out by cutting that in half because it bisects it.
Bisects it, so that's 6, 3.
And that's also perpendicular.
And perpendicular.
So it's 6,
3.
3.
So 3, 6, and you could use a number of things. Pythagorean theorem would be one of them to find that piece and then double. All right. Yes?
Not double. Square. You said to divide that piece and double it.
Yeah, because we're trying to find the chord. So I'm saying if we use the Pythagorean theorem to find this side, then double. All right. That was it then. I'm just going to collect this one because half of them are just drawing. There's only a few. If you want to check it, let's see. The ones for good answers, 12 through 15. 12 is 12 root 2. 13 is 24. 14 is 12. And 15 is 12 root 3. And half the rest are just drawings. There's a couple of them have numbers, but not many. All right. What's this chapter about?
Circles.
And lots of definitions.
No.
So more today.
I figured out how to do it, by the way.
Okay, cool. Now don't lie to me and tell me you looked at the book.
I didn't look at it.
All right,
I'm looking at the book. Let's see.
See if your proof is a real proof or not.
Well, it's a type of proof, but it's not the type of proof that we usually use.
Well, we'll see.
All right, I think I can figure this out. So let's see. M is a tangent tip. Good. Circle O at T. All right.
All right, McKinley, do me a favor. Go up to the board and read off what the homework is, because this is going to be the regular homework.
The homework.
Well, it's definitely going to be page 335 to 337, but the homework's going to be 1 through
11.
I gave them literally everyone exactly the same homework. Go figure. Now, did you just read regular or honors?
All right, honors.
1 through 11?
1 through 11.
All right. You guys get the same homework they got.
Oh, that means it's simple. Or wait, no, it's so small that it's going to be hard.
No, these are fine. It's a vocabulary intensive again. So I would say if there are confusing vocabulary words, it's today. None of the individual ones are confusing, but the words are so close to each other, 4 of them, that it can be confusing.
How do I prove this? All right.
You have your book open and you're cheating.
I don't have it open.
All right. Tangents. Once again, we're not talking about the trig ratio tangents. We're talking about perspectives or constructions where something touches another thing, something else in one individual spot.
Are you sure our trig can help us with this somehow?
Eventually, we will use trig with tangents, but not yet.
Not yet.
We haven't done a proof in a while. In fact, I'm already going to give it away. My next slide's going to give it away. All right, so before I do that, I'm not going to do that. Sorry, learners, you're not going to get to see this. I'll show you how I did the proof here in a second. Everyone else in class, we're going to do proof. So we are going to be given, this is Theorem 9.1, and it says, if you have a circle with a tangent, we'll call this tangent T, we'll call this line, what do you want to call it? What did I call it? M. And we call the center O. Okay, so the center O, that MTO is 90 degrees. In other words, it's perpendicular. That's what we got to prove. We got to prove that MTO is 90 degrees. Or you want to say that line M is perpendicular to segment OT.
You can make a right triangle.
You can, but you don't know that it's
All right, so that's what we're trying to prove, that this is 90 degrees. We don't know it's 90 degrees.
But you can start by making it a triangle.
We literally could. We'd have to make a new point, right?
Yeah, make a new point.
Okay, so what do you want to call your point?
6.
No.
4 is 22.
M.
M is the name of the line.
Yeah, but why don't we use M for this point?
Because then it'd be very confusing.
Exactly. H.
What do we want to call it? H.
Oh,
All right. So you want me to make a triangle? Okay, hero. Now what?
Well,
We could do that. We would say, H is on line M. Construct triangle OHT. Now what?
Yeah. Now that you have OHT, you can make another triangle on the other side.
Okay, so we could say something like, I have no idea if this will work, but we'll go with it for a couple seconds. Make another one, and I don't know. Do you want to make it the same or different way?
Same.
All right, so we could get that. I mean, I like the basic idea. As I'm just thinking out loud here. If we could somehow show that this triangle is congruent to this triangle, then therefore by CPCCC, that's congruent to that. Therefore, it would have to be 90 degrees.
Yeah.
All right, so we could absolutely make this. We'll call this point
Z.
Z. Okay. So we would get that. We would also get reflexive.
But we don't have. Well, if it's the same length away, then HT has to equal TZ.
Say it one more time.
If it's an isosceles triangle, HT has to equal TZ.
Yeah.
Why?
Because of the thing we did.
The thing.
Only if that's perpendicular.
Oh.
That's
Well,
not
you
enough.
could get H.
But that would be true if it was perpendicular.
Because the angle OHT and OZT are congruent because it's an isosceles triangle.
So we have yeah.
But you don't know it's a right triangle, so you can't.
Correct. If we didn't, then we would have a hypotenuse leg, by the way.
Well, we don't have a
So you
right
can't
triangle.
use that.
No, yes, you can.
Well, I mean, we can use it, but it just doesn't get us, you needed that angle.
But you have ASA.
No.
Yeah, you do, because there's one AS.
We don't. We all have is one angle. So, I mean, this is a good thought in the sense of that would be if we could do it. I mean, I would absolutely, if I didn't know how to prove this, I would probably think about that. But that's the issue. There is also another way of doing this to make this an angle bisector, right? We could do that, but then we would lose the fact that these would be congruent.
Right.
Like we could draw this, or we could draw this so that this angle equals that angle, and it would be either closer or farther. Then we would lose the part that was congruent. So we wouldn't get an ASA out of that. We would have an A, and an S. So we could do it that way.
No, we couldn't.
Sure, we could.
Because you would lose the two sides that are
No,
equal.
no. Don't care about that one because we still have reflexive. So we could get an A,
But you wouldn't
But
get that.
you wouldn't
You wouldn't
have
get
the
that one
bottom
because of the
angles, 'cause it's
it's
not an
isosceles
isosceles
triangle
triangle.
theorem.
So we can't do that. So I think we're out of thoughts for this one. All right. So that one didn't work.
You could temporarily assume that it's not perpendicular.
Any other thoughts?
Make another whatever this is, the bottom part on the other side. I can't remember its name right now.
You could just prove that it has to be perpendicular by saying that it can't not be perpendicular.
Oh yeah, you could do a switch. You could put M on top of the thing, like a copy of M. Make it perpendicular to M.
Maybe.
So
We could absolutely draw this so this is perpendicular. Okay.
But then would mean that MT is also perpendicular.
No, it wouldn't mean anything because I don't know what that angle is.
It'd mean that M is parallel to the line.
You
that
could
is
make
right.
the line, parallel to M, and then you'd have.
Okay. So instead of saying that, we could say make that dotted line parallel. We could absolutely do that. And then we have a transversal. That angle's congruent to that angle. I'm not sure where we're going with that, but so you got all these thoughts. If it was a longer day, we would go down this rabbit hole a bit further. That might work. I don't know.
You got to draw another one from O to the 1.
I think we would still have to do a triangle.
Yeah,
right?
you still have to make a triangle.
or two triangles, I'm saying.
Well,
You know, maybe, I don't know, just connect that and that to here, right? Maybe we get somewhere with that. Don't know. But we don't have enough time to go that. So this is the way the book does it. It's also the way that I would have probably done it. You know, it just kind of makes sense. We haven't done a proof in a while. In fact, we haven't done a what in a while? What kind of proof in a while?
The
paragraph proof.
No, those are regular proofs. That's just written, but a different type of proof. Proof by contradiction. So let's do a proof by contradiction. And you'll see how easy this.
That's what I was saying.
I know you were. I was ignoring you. All right. Proof by contradiction. Anna, after we get the given and where we're going, how do you do a proof by contradiction? Step number 1.
You restate the proof.
Except
You say that it's not.
say that's not true. So we're going to say the proof part is not true. So we say proof by contradiction, assume that
OT is not perpendicular.
okay, so that's what I'm going to do. So I'm going to assume by contradiction that OT is not perpendicular. That means that's not a right angle. Therefore, if it's not perpendicular, hey, I got a point and I got a line, you can always draw a perpendicular, right?
Yeah.
If I got a point, a line, you can always drop a perpendicular. So if this one isn't perpendicular, well, there's one that is. So what it says is to make that line. Now, period 2 could not wrap their heads around this because I drew this and I said, this OZ is now perpendicular. They're like, no, it's not. Look at it. And I'm like, yeah, well, that's a proof by contradiction. Clearly it's not, but that's what we're assuming is true. Or I should say, we're assuming that OT is not perpendicular to M. Therefore, there must be some one that I can drop down that is perpendicular. Now, hold on a second. Hold on. Make sure everybody can wrap their head around what we just did. McKinley?
All right. So
if this one is not, because that's what we're assuming, it's not, then there's got to be one that is, because if I have a dot and a line, I can always make a line that's perpendicular. So I just did this new dashed one. I'm claiming, clearly it's not, but I'm claiming it's perpendicular. Because if OT is not perpendicular, then where's the one that is perpendicular? There it is. I just drew it. All right, Jack, what?
Now you can say that since it's a triangle, the side opposite the biggest angle, which has to be TZO, equals longer than OZ. But since OZ...
Okay, hold on. Make sure everybody's on track here. So, triangle, right? In fact, what kind of triangle did I just make?
The right.
So what do you know about the side that is opposite the right angle? It's the longest side. Therefore, OT is the longest side. Let me write that. So OT is bigger than OZ. But M was a tangent. What do you know about a tangent? McKinley, what's a tangent?
a line that does touch the circle only once.
Well, where does it touch the circle?
The bottom.
Where does it touch the circle?
At the edge of it.
Where does it touch the circle? At T, right? So if T, and it's a tangent, if T is the only place it touches the circle, where is Z? Is it inside or outside?
Outside.
It's
Therefore,
outside.
it has to be longer.
Therefore, well, OT is a radius. And if Z is outside, well, it's got to be longer. Well, that contradicts what we just stated.
So then, therefore, OT is perpendicular to M.
And that's our contradiction. So, by the way, that was the previous reason. The side opposite the biggest angle is the biggest side. So, but Z is not on the circle. Therefore, we know that OZ must be bigger. That's the contradiction. And therefore, there are a contradiction that we assume is got to be false. And the only other, it's a binary choice. It's either perpendicular or it's not perpendicular. And we assumed it's not perpendicular. Therefore, it's got to be perpendicular. We just proved it. That's a pretty slick proof. And by the way, it gets away with, how do you show that if there's no numbers up there, there's no two triangles up there, how it's done. Okay, that's pretty good. All right, that's theorem 9.1. Write that one down. So all it basically says is if you have a tangent to a circle, then it forms a right angle. Except they don't say that, they say perpendicular. So if you have a tangent, then the radius is perpendicular to that tangent. And that's 9-1. Did I assign the corollary as a proof to write? Exercises 1 through 11. Yes. So the next thing we're going to do is corollary to this. This is question number 8. Actually, no. I didn't. You never proved it. Okay, we got to prove this. All right. Real quick proof. I'm glad because I proved it in period 2 as well, too. All right, we good on this? And there's only one, so they don't call it corollary 1. They just say corollary 9-1.
The last corollary.
No, we got plenty of other corollaries coming, but.
Are we almost done with postulates?
We've already done with postulates, right?
Don't know.
I know there's 14. Did you get all 14?
It's 15.
No, there's 14.
All right. Here we go. This is corollary 9-1. Look at the construction. So here's the basic idea. We got a circle. This time we have 2 tangents. Tangent PA and tangent PB. And what we're going to be able to claim, and this one's pretty easy, I'll prove it to you really quickly. We're going to be able to prove that these 2 are congruent. But look at the construction. They both come from point P. So they share a common point. And from that common point to the point of tangency, PA, PB, those 2 are congruent. And it doesn't matter where point P is. Point B can be anywhere outside the circle. If you have 2 tangents that go through point P, then from that point of intersection P to the point of tangency, those parts are congruent. Can you prove it, Jack?
I would say that A, P, A, and then whatever the center is congruent, and P. So
what do you want me to do?
So you'd make a kite because of that.
What do you want me to do first?
Yes, you would make a kite. Okay, hold on. So you would have.
What do you want me to do first?
Draw the center point.
I agree. Here's O. Now what?
Now draw a line from A to O and from
You
B
mean
to
make
O.
2 radii?
Yes.
What do you know about radii of a circle?
They're congruent. And also PAB, PAO and PBO are both 90 degrees.
Because, and that's why it's a corollary to 9-1, because that's what 9-1 says, is that these 2 are right angles.
So now you can say that since, wait, you're making a kite.
Don't make a kite.
What? What? It is making a kite.
Don't make a kite.
Yes, you do. Why not?
Make 2 triangles.
Oh, yeah. Okay, so put a line through P and O. And then you have 2 right triangles, and you can prove that they're the same.
And this line is actually the
reflexive. It's the shared.
And what is it to both triangles?
Perfect.
The hypotenuse.
Therefore, hypotenuse leg.
Right.
So therefore, CP/CTC done. Hypotenuse leg, CP/CTC done.
Don't you mean ASS?
Well, if you had been paying attention, I said that technically hypotenuse leg is ASS for 9 degree, but we just don't call it that. Okay.
I always call it that because of reasons.
I don't think so.
All right, we good? We good?
We can make.
Yeah, but the problem is that we haven't had any theorems about kites.
But we haven't.
So therefore, great, it's a kite. So what? You can't tell me anything about a kite because we haven't defined what it is. Our book has it. Maybe we could have gotten something, but even that, the kite doesn't say anything about the diagonal to the I mean, what we did was the easiest thing. Okay, we're not going to do the converse to the corollary. We're going to do the converse to 9-1. So the converse to 9-1 would be if it's perpendicular, then it's a tangent line. Okay, and this one's going to be proven exactly the way that we proved the first one, which was what? We got 10 minutes to finish this class. We're going to do it by proof by contradiction. So we're going to assume what? Okay, so L is not congruent. Therefore, if it's, I said congruent, therefore L is not tangent. So if it's not tangent, then what does that mean? If it's not tangent, then it's a secant.
Right.
Therefore, there's got to be another point that touches the circle. Where's that point? I don't know. We're going to call it point Z. And this is once again, not a second couldn't wrap their head around it. Like, well, that doesn't touch the, I know it doesn't.
Wait. How do you know that it's not just far out and not even
because it says that it's, where's a radius?
Perpendicular radius. Okay.
Yeah.
Well, I mean, it could be perpendicular radius. The radius would just go out.
Yeah, but if that is a radius and it's not a tangent, then it's got to touch somewhere else. If it's a radius, there's the radius.
You still draw a secant that's perpendicular to the radius.
You can, right?
Right.
But it says that that's on, it's a radius, but it's on the circle.
Oh.
Right? R is on the circle, not inside the circle. But you're right about if it wasn't, it could draw it like that. So it's a secant. So there must be some point somewhere that's the other point of the secant. So they call it Z and they draw it right. Now, just by convenience, they draw it right there. Once again, they couldn't wrap their head around this is really on the circle now, or at least that's what I'm claiming, right? So R and Z are both on the circle. The same basic kind of proof.
Well, that's the same. It's literally the same proof.
It's literally, well, no, it's different.
Well, because you have to say that Z
No, it's the same up to this point. Hey.
No, it's the same.
QR is what?
A radius. So then QZ has to be a radius, but Z is outside of the circle because.
Yeah. So if this is 90 and this is a radius and this is a radius and that's congruent to that, therefore it's really what kind of triangle?
An isosceles triangle.
Therefore, what's this angle right here? QZR, online learners.
90.
Well, what's the problem with that?
It can't be.
What's the problem with that?
Because all of the interior angles of a triangle add up to 180, and you already filled up 180 with just two angles.
And there's your contradiction.
Yay.
So we made two radii, that makes it an isosceles triangle. If it's isosceles, then that means that the other angle is 90 because this one was 90. And then that's our problem is that, well, you can't have.
Well, you can also say that because Z has to be outside of this.
No. Well, no, this is the way you got to say it. This is the way you got to say it. What you said, no, because of what you said before, right? Okay, that's it. QED, done. All right, write that one down, 9-2. So it's biconditional, but our book never writes any biconditionals. So if you have a line that goes through a radius, that point T, and it makes a 90-degree angle, then it's a tangent. Oh, I forgot that part. Ooh, down to 7 minutes. There's 4 words we got to cover.
4 words. There's a whole chapter.
And each one is 3 words long.
Okay.
Or maybe it's 2 words. No, it's 3 words.
Okay.
All right, we're going to do this really quick. Really quick. I will slow down to make sure you understand it, but we may have to have you write down the word and you copy the definition down on your own tonight for homework. All right. All right. So here's the last 4 of them. Recall from last class we had inscribed, we had circumscribed, and just remember one picture gives me both. Right. This is an inscribed circle. This is a circumscribed, or the triangle circumscribes the circle. So if you're talking about the outside, circumscribed, inside, inscribed. All right. Here's the 4, and it's actually 6 to mess with you. Okay. Tangent, yes.
Yeah.
Right. Well, it turns out you can put another circle on it, and so therefore this line is not going to be called a tangent. It's going to be called a
Double tangent.
common tangent.
It doesn't seem that common.
Oh, by the way, it could be more than 2. No, common tangent. It's got 2 or more circles that are tangent to the same line. All right, like I said, we're going to write down the definition, otherwise we're running out of time. Here's the issue. Here's the first of 6. It turns out there's 2 flavors of this. You ready? All right, the 2 flavors are this. Right? If I instead start with a line, start with a circle. If I draw the 2 circles and I play connect the dots with their centers, you see what I did? Now I'm going to draw the two types of common tangents. The first one, well, it looks like that, right? Doesn't have any interaction with this. There's another way of drawing that common tangent that still only touches the circles in one places. You see that? I'm touching this. The blue one touches the small circle there once, touches the big circle there once. What's different between the blue one and the red one? The blue one intersects this line that connects the two centers of the circle. We're going to call the red one a certain type of common tangent. We're going to call the blue one a certain type of it. All right, here are the words. All right, if it goes through that common center, we call it a common internal tangent. And if it doesn't, if it's the other flavor, guess what we call it? And you can finish the definitions on your own. Does this dotted line have, literally anything to do with the tangent line though? Do you need the dotted line to draw the tangent? And the answer is no. The dotted line helps with the definition, but it has nothing to do with the common tangent. The common tangent is RS here. The common tangent here is AB. The dotted line there, unnamed, it's not part of the construction, it's part of the definitions, if that makes sense. Okay, cool. So there's 3 of 6. If it was just those two, you wouldn't get it because common internal, common external. It makes perfect sense. I'm going to give you 2 more. It's technically 3 more. I'm going to give you 2 more. The words sound exactly the same. It's completely different. 2 more. It's going to sound exactly like common internal, common external. All right, here we go. Tangent touches a circle at one point, right? Well, we're talking about a line that touches a circle. Well, circles can touch other things in one spot as well. In fact, they can touch each other in one spot. So watch this. These are called tangent circles. And these are circles that touch each other in one spot. For instance, ready? For instance, 2 flavors again, that construction or that construction. So the other one was called a common internal tangent, whatever. These are called tangent circles. The 2 flavors, they got words that are just too close to this. All right, here we go. Here's the first one. When the 2 circles touch each other, right? And where they touch each other, right, is externally, we're going to call it externally tangent circles. So we have common external tangents and we got externally tangent circles. Oh, dear Lord, it's just too close together. This is why if it's in your book of truth, you'll forget which is which. Now, what in the world has that line got to do with this whole thing? So basically what it's saying is that if that point of tangency intersects a line that can be drawn between the 2 circles, that's what meets the definition. I hate this definition. For me, visually, it makes perfectly sense that this is called an externally and the other one is called because the circles are inside of each other. That makes perfect sense to me. I don't need that line. And oh, by the way, you don't even need the line because it's not part of the calculation or not calculation. It's not part of the construction. It's part of the definition. So there's your externally tangent circles, and the other one is when the circles are nested within each other. They still got that red line there. It's part of the definition. So the definition of an internally tangent circles are circles whose tangent does not intersect the line between the centers. And like I said, that red line can, what the heck, I don't need that red line. These are the internal ones, and the other ones are the external ones. All right, there's your confusing terminology. Tonight for homework, it's a mixture of what we did. There's a couple things that you have to look at a diagram and whatnot. I don't believe there's any drawing at all. No, 9 is a draw. I think that's the only one. There's a picture. This is trivia. If you have nothing but congruent circles, how many circles would circle a circle?
The kissing number.
6, 8,
6.
There's your picture. How many, if all the circles are the same, how many circles circle a circle?
not all of them.
6.
6.
And it turned, now they all gotta be the same size. So it turns out that it's 6. It's an interesting, it's in the book and I threw it in there because it's interesting.
And the kissing number raises with dimensions. Like that's 6 for it's like 2 dimensions, but it's like 12, I think, for 3 dimensions.
I don't know. I don't
And
know what
it's
the answer to that is.
24 for 4 dimensions, and then you have a range for going up. Like they can't actually figure out the exact number, except for 8 and 24 dimensions.
I'm traveling to the 4th dimension this weekend.
Yes. Tell me what it's
All right, stack 4 chairs. 4 chairs. And we're out of here. Well, right on time. Ben, you did not show up. Is that correct?
Dear Mr. Testament,
Yes, Mr. C, that's correct. All right, Ben. Any questions? Oh. Have a good weekend, Ben. Okay, you too. Yes, I do.